OpenAI's Whisper is a genuinely great speech-to-text model, and it is slow. If you have ever run the base or large model over an hour of audio and watched it crawl, you know the pain. fasterwhisper fixes that. It gives you identical accuracy at about 4 times the speed on the exact same hardware, and it uses less memory too. Let me be really clear about what it is and is not, because people get confused. It is not a different model. It is not a smaller or a dumber model. It is the same whisper weights, the same tiny, base, small, medium, and large V3 checkpoints you already know, just re-implemented on a much faster inference engine underneath. Same transcript quality, a fraction of the weight. In this video we do the whole thing, end to end, install it, load a model, get your first transcript out, pull out per word timestamps, pick the right device and compute type for CPU or GPU, and then batch long files for a huge extra speedup on top. Setup, first transcript, and word timestamps in about 10 minutes. Let's go. So why is fasterwhisper actually faster? It comes down to the engine underneath. The original OpenAI Whisper package runs on PyTorch, which is fantastic for research and training, but it carries overhead you do not need at inference time. fasterwhisper is a clean re-implementation of the same model on top of cTranslate 2, which is a fast inference engine built specifically for transformer models. Same weights, same accuracy, just a much leaner runtime designed to do one thing well, run the model forward, fast. On top of that, cTranslate 2 supports int8 quantization. Quantization means storing the model's numbers in 8-bit integers instead of full precision floats, which shrinks the model in memory and speeds it up even more, with almost no measurable accuracy loss on speech. Put those together and you get up to about 4 times faster and noticeably lower memory, on the same audio and the same machine. And to say it one more time, because it matters, the model sizes are exactly the ones you already know, tiny, base, small, medium, and large V3. You pick the size for the accuracy you need, and you let the engine handle the speed. Installing is genuinely one line, pip install fasterwhisper. That is it. It pulls in cTranslate 2 and the tokenizer for you automatically, so there are no extra steps to chase. You do not install OpenAI Whisper separately, and, importantly, you do not need FFmpeg on your system path for basic use, because fasterwhisper decodes the audio with a bundled library called PYAV. That alone removes the single most common setup headache people hit with the original Whisper. Then in your Python code you import exactly one class, from faster_whisper import Whisper model. That Whisper model class is the entry point for everything you are going to do. If you plan to run on a GPU later, that is where CUDA and CUDNN come into the picture, and we will get to that, but for a plain CPU transcription there is nothing else. No build step, no compiling, no system packages. Pip install fasterwhisper, import Whisper model, and you are ready to transcribe. Alright, here is your first transcript. You create the model with Whisper model, passing 3 things, a model size, a device, and a compute type. On a CPU that looks like Whisper model of the string base, device equals CPU, compute_type equals int8. Then you call model.transcribe, and you pass it your audio path plus a beam_size of 5, which is a good default for accuracy. That call returns 2 things at once, segments and info. Now here is the single most important gotcha in the whole library, the one that trips up almost everyone the first time. Segments is a generator. Transcription is lazy. When that transcribe line returns, nothing has actually been transcribed yet. The real work only happens as you iterate. So you write for segment in segments, and it is that loop that drives the transcription forward, chunk by chunk. Each segment object gives you .start, .end, and .text, where start and end are times in seconds, as floats. The info object, which comes back immediately, carries info.language, info.language_probability, and info.duration, so you get automatic language detection and the audio length for free, before you have even looped. Print segment.start, segment.end, and segment.text inside that loop and you have a working timestamped transcript. Segment-level timestamps are great, but very often you want word-level timing. Think subtitles that highlight the current word, karaoke-style captions, or aligning a known script back to the audio. I care about this a lot, because this channel's own video pipeline uses a Whisper-based aligner for exactly that kind of word timing. Getting it out of fasterwhisper is one keyword argument, you pass word_timestamps equals true to transcribe. Once you do, every segment gains a .words list, and each entry in that list is a word object. Each word carries .start, .end, .word, and .probability. So the pattern is a nested loop, you loop for segment in segments, then inside that you loop for word in segment.words, and you print word.start, word.end, and word.word. That fourth field, probability, is a genuinely useful bonus. It tells you how confident the model was about that specific word, on a 0 to 1 scale. So when you are building captions you can flag, color, or drop the low-confidence words instead of trusting everything blindly. That one flag turns Whisper from a paragraph machine into a precise, word-aligned timing tool. Device and compute type are your two main levers for trading off speed and accuracy, so let's be deliberate about them. On a CPU, use device equals CPU with compute_type equals int8. That is the smallest and fastest option, and thanks to quantization it barely costs you any accuracy, so on CPU it should be your default. If you have an NVIDIA GPU, switch to device equals CUDA with compute_type equals float16, which is the fast and accurate choice on the GPU. Just know that the CUDA path needs CUDA and CUDNN actually installed on your machine, and that is the usual source of setup friction, so if you hit a library not found error, that is where to look. There is also a middle option, int8_float16, a hybrid that stores weights as int8 but computes in float16, which can be a nice balance on some GPUs. The simple rule of thumb, int8 is the single biggest speed lever you have, and it hardly touches accuracy, so on CPU reach for it first, every time. And one more free win, if your audio has long silent stretches, like a meeting recording with dead air, add vad_filter equals true. That turns on voice activity detection, which skips over the silence instead of transcribing it, saving you even more time on top of everything else. For long files there is one more big speedup available, and it is worth the 2 extra lines, batching. fasterwhisper ships a batched inference pipeline. You import it, from faster_whisper import batched inference pipeline, then you wrap your existing model with it, and you transcribe through the pipeline with a batch_size argument. Concretely, batched_model equals batched inference pipeline of model equals model, reusing the exact Whisper model you already built. Then segments, info equals batched_model.transcribe of your audio, with batch_size equals 16. Notice it returns the same segments generator and the same info object as before, so every bit of your iteration code stays identical, you change nothing downstream. Under the hood, instead of processing the audio strictly one chunk after another, the pipeline runs multiple chunks through the model in parallel. On a short clip you will not notice much, but on a long podcast, a lecture, or an hour-long interview, that parallelism can be dramatically faster. Same model, same weights, same accuracy, you are just squeezing far more throughput out of the hardware you already have. So let's put the whole workflow in one place. 1. Install with pip install fasterwhisper, one line, no ffmpeg needed. 2. Load a model with Whisper model, passing size plus device plus compute type. 3. Call transcribe to get back a lazy segments generator and an info object, and remember, you must iterate the generator to actually run the transcription. 4. Add word underscore timestamps equals true whenever you need per word timing, and use the probability on each word to judge confidence. 5. Pick int 8 on CPU or float 16 on CUDA, and add VAD underscore filter to skip silence. And 6. Wrap the model in a batched inference pipeline with a batch underscore size for long files. That is it. Same whisper accuracy you already trust, roughly 4 times the speed, all thanks to the ctranslate 2 engine underneath. If you want more practical, everyday Python like this, there is a free Python interview questions guide linked down in the description, and a Python Power Pack if you want to go deeper with snippets and idioms. Now go transcribe something.